All right, let's talk about chapter 16, which is about nuclear fusion. Okay, so we're going to cover where the possible sources of energy that come from the sun and how Einstein helped answer that question and what's going on the inside of the sun. Okay, so sources of sunshine. So the initial people trying to explain where all this energy comes from. You can stand outside, feel the heat, you can try to calculate it. It's a huge amount of energy reaching the Earth. You're trying to explain how to do it. How do you explain 4 times 10 to the 26 watts of energy, which is a very bright light bulb? You could power a trillion cities with a trillion 100-watt light bulbs, and it's a bunch of light bulbs. So anyway, we couldn't figure out how to explain how this energy comes from. And we were trying to figure out how that amount of energy can come from a star, this star, right, for as long as it's been around. How could you possibly get that amount of energy? So people thought, well, wood, coal, gasoline, another fuel, maybe there's chemical energy like that, to try to calculate what that is. There's no way. And you could only present or power it for a few thousand years at the rate of the burning based on what we knew about how you could get chemical energy out of a thing. But we knew that Earth was at least 4 billion years old, so the sun must have been shining for that long to keep Earth warm for that time while life developed and all that stuff. So there's no way that a chemical burn could produce the energy. So then another idea was this conservation of energy, and says, okay, well, conservation law says that energy can't be created or destroyed, only transformed. So we must be transforming something into this energy. What are we transferring? And so one thought was that the sun, this size, is slowly shrinking. And as it gets smaller and smaller, I'm exaggerating there, but as it gets smaller, the change in gravitational energy from there, as you push it closer and tighter together, it's going to heat up, and maybe that's what's causing it. So maybe it's the conservation of energy from gravity, and maybe gravity is the thing doing the falling inward is causing the sun to heat up. And by calculating that, what it would take, they say, hey, we actually have a number and we can do it, and it seems reasonable. We got 100 million years out of it. Maybe that was enough. Maybe the Earth was less than 4 billion years old at that time. They still thought that could be a possibility. Okay, but now when we got to the 4 billion years, it's like, well, 100 million years doesn't quite cut it either. What's going on? So then Einstein comes along and he says, well, wait a second. We can transform energy by conservation of energy. We just turned mass, M, into energy, E. And if you can convert a tiny amount of mass into energy, that tiny amount of mass times the speed of light squared is the amount of energy you get out of it. That's a huge amount of energy coming out of an object. E equals mc squared. Pretty amazing. Okay, we've got some conversion factors here that you can do to do some conversions. There's a thing about Einstein there. Okay, so he came up with E equals mc squared, and that's what the sun is doing. It's converting hydrogen into helium, and there's a mass difference there, and E equals mc squared, so the difference in mass, the sun is basically eating itself, losing mass slowly over time as it turns that mass into pure energy and radiates it out into space. Okay, so in order to understand how the sun does this, the process of fusion, we've got to understand a little bit about fundamental particles. So you have a proton, and you've got an electron that orbits the proton. That's a hydrogen atom. Okay, so you've got your proton, you've got your electron. There's also a thing called a positron, and it's just a positively charged electron. It's the same as an electron in every other way, except its charge. And that's what antimatter is. They're the same as every other particle. It just has the opposite charge from their matter counterpart. So you've got an electron, you've got an anti-electron, which we call the positron. You've got a muon, you've got an anti-muon, you've got a proton, you've got an antiproton. Everything has an antiparticle. The universe that we know is filled with matter, but there's still antimatter floating around every now and then. It can be created when you have E equals mc squared. Okay, then there's a special particle, the neutrino. So why do we care? Because during the energy process of the sun, we have protons, electrons, positrons, and neutrinos coming out, and so we need to be able to talk about those things. So this idea of the neutrino is carrying away some of the energy that's left over from the sun. So there's your particles. A single atom could have a proton, a neutron, electron in it, and during the conversion process, you can convert protons, and when you combine them into their atoms or do other transformations, you usually get a neutrino and an electron or an anti-electron or a positron shooting out. Okay. Mass of the neutrino, we don't know what the mass is. We know it's not massless, and we know it's very small. So it's super duper small, which makes it very difficult, to read what the mass is. So we're trying to figure that out right now. Actually, that's cutting edge. Okay, so the atomic nucleus, okay, you've got protons, and when you have protons, they don't want to be next to each other because they're both positively charged. So the way you get protons to stick together in an atom, so for example, this is hydrogen, and this is helium. And how do I know that? Because let's go to periodic table. Okay, click on that. Periodic table. Take a look at the periodic table of the elements. Oh, I like this one. Nice, simple. Okay. Come on. Oh, it's some guy's shirt. Lame. Really? Okay, gee whiz, I'm going to have to design a new periodic table. These are all horrible. Okay, so we've got in the top left here, let me do this. So in the top left, we've got hydrogen, and in the top right, we've got helium. Notice hydrogen has a 1, helium has a 2. That number is the number of protons in the nucleus. So if I look at lithium here, how many protons make up a lithium atom? Oh, it's 3. How many protons make up the iron atom? Oh, it's 26. How many protons make up boron? 5. Boring. Okay, so every atom on here, every one of these, they're all the same as each other. The only thing that's different is how many protons they have in their nucleus. Okay, so if I've got an iron atom, okay, which has 26 protons jammed together, but I just told you that positively charged objects don't like to be next to each other. How do you explain that? Okay, because opposites attract and like charges repel. So it's like putting 2 North Pole magnets together. They repel each other. So how does this work? Okay, it turns out if you get a proton this close, they repel each other. If you get a proton and another proton that close, they actually stick together because the strong force can only reach out about this far, okay, like little Velcro or T-Rex arms. If you get the protons to within that radius, then the strong force will take over, and they reach out, grab each other, and combine, and then they get stuck together. That's how you get heavier atoms. So that's the process of sticking protons together is called fusion. The reverse case of sending a particle in and splitting atoms into pieces is called fission, and that's how we use, that's where nuclear energy comes from on Earth. Nuclear power plants are doing fission. They're splitting the atom to get the energy out of it, whereas fusion energy, they're putting it together. The sun is fusing nuclei together. Okay, so here's fusion. You're turning these two guys, you're combining them into produce one. In fission, you're taking something like uranium, which has 92 protons in it, and smashing it, or breaking it apart into 2 smaller atoms. Okay, so this is nuclear energy today on Earth. This is fusion energy in the sun. Okay, so here's about this fusion. You need a high temperature in order for protons to fuse. And so that's the idea, is that the core has got to be at least 10 million degrees Kelvin before you have your temperatures. And in the sun, the core is near 15 million Kelvin. Okay, so all the energy coming from the sun occurs within about 150,000 kilometers of the sun. So within 10% of its volume, that's the only part where the fusion is actually taking place, because you need super duper high fusion reactions. Okay. And okay, so there's your So the process of generating energy in the sun is known as the proton-proton chain. Okay, and the proton-proton chain is just the process of combining hydrogen atoms in order to get helium eventually. So you start with two hydrogen atoms, they combine, they merge into what's called a deuterium atom, which is hydrogen with a neutron in it. And then notice you get a neutrino and a positron popping off. So those go off into wherever. And now you've got a H2 atom. And H2 is an isotope of hydrogen. An isotope is just an element with different numbers of neutrons. So H1 is just hydrogen. H2 is an isotope of hydrogen. It's got a neutron. H3, if there was one, is called tritium, has 2 neutrons in it and 1 proton, so it's still an isotope of hydrogen. So when hydrogen and its isotope deuterium, when they merge, you get helium-3. And we call it helium-3 because it has 1, 2, 3 things in its nucleus, nucleons in its nucleus. Okay, and then you get some helium-3s left over. When they combine, then you finally get helium-4, and that's where the final step in the proton-proton chain happens. You get helium building up in the core, and then a couple more hydrogens bouncing around to do more fusion. Okay, so there's 3 steps to the chain. Hydrogens combine into heavy hydrogen and 1 hydrogen combine into helium, and then this happens several times, and then eventually you get 2 of the middle reaction here, which then you get 2 helium-3s, and then that combines into helium-4, and then a couple of hydrogens pop off. So this here is just a text version of these 3 pictures. So your step 1, step 2, step 3, and that's where you stop, and your helium starts building up in the center of the sun. And then you calculate the mass difference here, and then you do E equals mc squared, and you get 6 times 10 to the 14 joules from the leftover mass, because the hydrogen atoms you combined in order to get your helium, the difference between them, the mass left over, is this tiny little atomic mass units, 0.02862 atomic mass units. That equals, put that into kilograms, that equals this amount of energy. Okay, so that's a huge amount of energy. That's called the proton-proton chain. When we talk about high mass stars, we're going to talk about the CNO cycle. So just keep in mind the proton-proton chain is for low mass stars. Okay, fusion on Earth, there's something called ITER. And ITER is a tokamak, and it's designed to create a magnetic field which contains a plasma in this little ring here around, and then you turn the magnetic field up very high and then zaps this and then creates a fusion reaction. It will never work probably, but they're working on it. Okay, so then inside the sun's a plasma. Make sure you remember what that is. The sun's stable because the pressure outwards from the force is balancing the force of gravity. That's what makes its size the size it is. The sun's not cooling down, it's maintaining its heat. There's the radiative zone and the convective zone. So again, that convection is making that granulation on the surface. Photons, in order to get out of the sun, they bounce around a while between all the electrons. And neutrinos, though, the difference between a neutrino, so in those reactions you get photons created, but you also get the neutrinos created. The neutrinos are a particle that weakly interacts with stuff, so it doesn't hit anything. The space between the atoms are so small that the neutrino can find a path without seeing them. Even a neutrino could go right here, and the odds of them hitting something is very low. So neutrinos created by a fusion reaction leave the sun immediately. Every other thing created by the sun takes a while for its energy to actually get out of the sun. So that's just an interesting point. Okay, so there's your star, there's your sun, there's your fusion taking place in the core within 10% of the volume. And then here's your temperature as a function of distance. So it goes from 15 million Kelvin to 5,000 Kelvin on the surface. The density rapidly falls off until you get to the surface. So it's very dense at the very centermost part of the core. And then most of the light that we see comes from the radiative zone. So we don't see a lot of light coming out of the core that we see. And then the percentage of weight. So you've got about 25% hydrogen at the very center of the core, and then, let's see, yeah, and then the other part of that's going to be your helium left over. Okay, so we can determine what the inside of the sun looks like by looking at this Doppler effect, and the surface of the sun has these red, blue things because the light's getting shifted red or blue, and that's called helioseismology, which is the process of looking at the density waves within the sun. It's the same way we determine how the inside of the Earth, what it's made out of, by measuring waves as they bounce around from earthquakes. Okay, so yeah, this is just an interesting thing about the sunspots, the convection that's going on here and the magnetic fields and things, what we can determine from helioseismology, how it works. Okay, so solar neutrinos. Here's a cool experiment. All these things are underground, these big chambers to detect neutrinos deep underground, in order to understand where the neutrinos are coming from. It turns out that the neutrinos oscillate from one type to another. So this neutrino oscillations is an active area of research, very, very important to understanding. So there's 3 types of neutrinos: muon neutrino, electron neutrino, and a tau neutrino. You don't have to know that. But the neutrino oscillations are the neutrinos that come from the sun should be a certain type of neutrino, but there's only a third or 2/3 of the ones we expect. Only a third of the ones that we expect come from the sun are electron neutrinos. So 2/3 turn into something else on their way. And that's the first sort of evidence that the neutrino is not massless, it has some mass. Okay, so anyway, so learn a little bit about the history of why the sun's energy is a problem, why it took so long to figure out. And then we finally figured out with the E equals mc squared, so make sure you understand what that's doing. The solar interior, talk about how we can use the helioseismology to understand what's going on inside the sun by studying these pulses on the surface. Okay, and then how measuring the neutrinos coming from the sun allows us to measure what's going on inside the sun. And don't forget what fusion is and how that works. Okay, proton-proton chain.